is Dr. Krishnaveni from Department of Chemistry, K.B.N college. I would like to discuss about the solid state and the properties of solids. So before going to that, first of all, let us discuss about symmetry in crystals. So unlike liquids and gases, solids have both definite shape and volume. These are characterized by rigidity, incompressibility, slow diffusion and mechanical strength. So these properties of solids are due to the fact that the particles that are present in the solids, that may be ions, atoms or molecules, they are very closely packed and held together by strong attractive forces. So because of that reason, these particular properties belongs to solids. So coming to the crystallography, it is nothing but a branch of science which deals with the geometry properties and structure of crystals and crystalline substances. So mainly the crystallography is based on three fundamental laws. So the first one is law of constancy of interfacial angles. According to this law, the size of the faces or even shape of the crystals of the substances may vary widely with the conditions of crystallization, but the interfacial angles between any two corresponding faces of the crystal are always constant, which means that whatever be the shape or size of the faces of the crystal, the interfacial angle between any two corresponding faces of the crystal are always constant. So this may be explained by taking an example of sodium chloride crystal. So in the case of sodium chloride crystal, the interfacial angle is found to be 90 degrees irrespective of the size and shape of the crystal. See, suppose if I take these hexagons, whatever be the size of the hexagon, the interfacial angle between the two faces is constant. Next law, the law of rational indices. This law states that the ratio between the intercepts on the axis for the different faces of crystal can always be expressed by rational numbers. Suppose if I take like OX, see here it is OX, OY and OZ be the three crystallographic axes of this unit cell ABC. ABC is considered as a unit cell. OX, OY, OZ be the three crystallographic axes, and LMN be the planes of the crystal. See, LMN be the planes of the crystal. The unit intercepts are A for OA, see A for OA, and B for OB and C for OC. So the intercepts will be OL, that is equal to 2A. The intercepts will be OM, see OM is equal to 4B, 1, 2, 3, 4. So it is 4B, and the intercepts ON 3C, 1, 2, 3, 3C. So the unit intercepts are C for OC, B for OB, A for OA. Therefore, the total intercept will be OL. OL is nothing but 2A. OM is nothing but 4B. OC is nothing but 3C. Thus, the intercepts for the plane LMN are, see, the plane LMN. The plane LMN are the intercepts for the plane LMN are 2A, 4B and 3C. 2A, 4B and 3C. So, where 2, 4 and 3 are simple integral whole numbers which are known as these indices of the plane LMN. Here 2, 4, 3. These three are the simple integral whole numbers and are known as these indices of the plane LMN. Okay. Next, these indices may be simple integral whole numbers or may be fractional numbers, or sometimes it may be infinity also. So these simple integral whole numbers are known as these indices, and they may be whole numbers or may be fractional numbers or even infinity. So coming to the Miller indices. Miller indices HKL of faces of a crystal are reciprocal of the intercepts of the faces on the these indices. Simply, Miller indices are the reciprocal of these indices. Obtained, that means Miller indices are obtained by taking the reciprocal of these indices and multiplying throughout by the small number in order to make all reciprocals as integers. Suppose if I take these indices of the plane infinity A, 2B and C. Here the these indices are infinity, 2 and 1. Then in order to get Miller indices, we have to take the reciprocal of these V's indices. Then the Miller indices are 1 by infinity, 1 by 2, 1 by 1. So 1 by infinity is nothing but, so multiplying by 2 in order to get whole integers. 1 by infinity is nothing but 0. So by multiplying it by 2, it comes to 0. 1 by 2, which is by multiplying 2, we can get 1. 1 by 1, by multiplying it with 2, we can get 2. So 0, 1, 2 are the Miller indices of the plane. Therefore, the distance between the parallel planes in a crystal DHKL is defined as DHKL is equal to A by root H square plus K square plus L square, where A is the length of the cube and H, K, L are the Miller indices of the plane. Next, the law of symmetry. It states that all crystals of substances possess the some elements of symmetry. The three important elements of symmetry are plane of symmetry, axis of symmetry and center of symmetry. So first one is the plane of symmetry, which can be defined as it is an imaginary plane which divides the crystal into two identical halves. For example, if I take a cube is having two types of plane of symmetries. First one is the rectangular plane of symmetry and the other one is diagonal plane of symmetry. So rectangular plane of symmetry means these are the planes which are parallel to opposite faces. See, suppose if I take a cube, this is one face and this is another face. So these two are the opposite faces. So since a cube crystal has 6 faces, so it has 3 rectangular plane of symmetries. So by taking a plane passing through two opposite faces, if I take a plane which is passing through two opposite faces which divides the cube into two identical halves. For each cube we have 6 faces. So we have 3 rectangular plane of symmetries. Next one is diagonal plane of symmetry. So these are the planes which are passing through the opposite edges. See, if I take this is the cube and these are the edges. So for each cube there are 12 edges are there. So opposite edges, a plane, if I consider a plane which is passing through two opposite edges which divides the crystal into two identical halves and which divides the cube into two identical halves. So that cube has 6 diagonal plane of symmetries. So for each cube there are 3 rectangular plane of symmetries and 6 diagonal plane of symmetries. So for a cubic crystal, totally there are 9 plane of symmetries. 3 are rectangular plane of symmetries and 6 are diagonal plane of symmetries. So coming to the axis of plane of symmetry or axis of symmetry, it is an imaginary line about which the crystal may be rotated so that it represents or it presents the same appearance more than once in a complete rotation through 360 degrees. Suppose if I take an axis which is passing through opposite phases of a cube, if I rotate the cube through this axis, so appearance occurring, identical appearance occurring during the complete rotation of 360 degrees. So axis of symmetry is of 3 types. One is 4-fold axis of symmetry. So it is nothing but an axis passing through the center of two opposite faces of a cube and rotating about this axis through 360 degrees. The original appearance is repeated 4 times for every 90 degrees. So see, opposite faces. Next one is 3-fold axis of symmetry. It is nothing but an imaginary line passing through the opposite corners of a cube and rotating the cube through 360 degrees. About this line, the original appearance is repeated 3 times. So this original appearance is represented as a result of rotation through 120 degrees. Since a cube has 8 diagonals, there are 4 3-fold axis of symmetries. So next one is 2-fold axis of symmetry. It is an imaginary line passing through the opposite edges of a cube. On rotating about this line through 360 degrees, the original appearance is repeated 2 times. that is the original appearance is represented for every 180 degrees rotation. Since a cube has 12 edges, there are 6 two-fold axes of symmetries. So totally for a cube has 3 four-fold axes of symmetries and 4 three-fold axes of symmetries and 6 two-fold axes of symmetries. So totally 13 axes of symmetries are present for a cube. 6-fold axis only. This is possible only in the hexagonal crystals. It is a line passing through the center of two opposite hexagonal faces on rotating crystal through 360 degrees. About this line, original appearance is repeated for 6 times. So the original appearance is repeated for every 60 degrees rotation. So this is axis of symmetry. Next, coming to the center of symmetry, it is a point in the center of the crystal. If any line drawn through it, it intersects the surface of the crystal at equal distance on either side. A crystal has only one center of symmetry. The total symmetry elements in a cubic crystal are totally 23. Among them, 9 plane of symmetries, 13 axes of symmetries and 1 center of symmetry. Next, space lattice. The regular arrangement of an infinite set of points in a space is called as space lattice. The space lattice may be one-dimensional, two-dimensional and three-dimensional. So coming to the unit cell, the smallest repeating pattern from which the lattice is built is known as unit cell. Unit cells are of following types: simple unit cell, face-centered unit cell, body-centered unit cell and end-face-centered unit cell. So what is meant by simple unit cell? So in this type of unit cell, atoms, ions or molecules which are considered as points are presented only at the corners of the unit. See, this is an example of simple unit cell. Here the atoms, ions or molecules which are considered as point, they are present at the corners of the unit cell. See, like this, only corners, the points are present. So next one is face-centered unit cell. In this type, the points are present at the corners as well as the center of each of the 6 faces. See, this is face-centered. Here the points are present at the corners of the unit cell and as well as they are also present at the center of the every face. See, center of the every face, each point is present. So this is face-centered unit cell. Next one is body-centered unit cell. In this type, atoms, ions or molecules are present at the corners and additional point is present at the center of the unit cell. So this is body-centered unit cell. Here the points are present at the corners and as well as at the center of the unit cell. Next one is end-face-centered unit cell. In this type, the points are present at the corners and as well as at the center of 2 ends. See, this is the end-face-centered unit cell. Here the points are present at the corners, see, and as well as end faces. Here is one point is present and here is one point is present and these are 2 end faces. So this is an end face centered unit cell. So there are 4 types of unit cells. Simple unit cell. In this, all the points are present at the corners of the unit cell. Face centered. In this, the points are present at the corners of the unit cell and as well as at the center of each face of the unit cell. And this is body centered unit cell. Here the points are present at the corners of the unit cell and as well as at the center of the body one point is present. In the end face centered unit cell, here the points are present at the corners of the unit cell and as well as 2 points are present at the opposite ends of the opposite faces of the unit cell, and it is nothing but end face centered unit cell. So coming to the lattice point, the points representing the atoms, molecules or ions in the unit cell are known as lattice points. So this one is one lattice point. This is. So the total number of lattice points for a simple unit cell, the total number of lattice points present is 1. For end face centered unit cell, the total number of lattice points present is 4. For body centered, the total number of lattice points are present is 2. And for end face centered, the total number of face points are lattice points are present is 2. So coming coming to the most important topic, which one is X-ray diffraction or crystal structure, Bragg's equation. So the scientist Bragg derived a simple relation between the wavelength and the distance between the two successive atomic planes and the angle of reflection theta, which is known as Bragg's equation or Bragg's law. So the scientist Bragg derived a relation between the wavelength lambda and the distance between the two successive planes. Suppose if I take one plane 1 and this is plane 2, and the distance between the two successive planes is taken as d. This is d, and the angle of reflection theta here, this is the angle of reflection theta, is known as Bragg's equation or Bragg's law. So in order to derive Bragg's equation, consider two waves 1 and 2, wave 1 and wave 2, which is incident on plane 1 and plane 2 respectively at an angle theta. The path length BZ dash is larger than the path length AOA dash. BZ B dash is larger than the path length AOA dash. BZ B dash AOA dash. So the path length AOA dash is lesser than the path length BZ B dash. So the path difference is nothing but CZ plus CZ plus DZ. This is the path difference, CZ plus DZ. If lambda is the wavelength of the incident X-rays, so if lambda is the wavelength of the incident X-rays, then CZ plus DZ is equal to n lambda. CZ plus DZ is equal to n lambda, where n is the whole number. Since the triangles OCZ and ODZ are congruent, the triangles OCZ and ODZ are congruent, therefore CZ plus DZ, therefore n lambda is equal to 2CZ. So CZ is equal to n lambda by 2. For the triangle OCZ, sin theta is equal to CZ by OZ. For the triangle OCZ, sin theta is equal to CZ by OZ. So CZ is equal to OZ sin theta. Therefore CZ is equal to d sin theta. So substitute equation 1 in 2. By substituting equation 1 in 2, we can get n lambda is equal to 2d sin theta, where n is equal to 1t3, and the above equation is known as Bragg's equation.